So on page 138. And it says, repeat exercise 5 for C, and that's consider the production X equals C X plus D. And in our case, they're going to have a different C and a different D. And use the inverse matrix to determine the production level. So what you have to do with this is, just like before, you got to go X minus CX equals D, and then do the I minus C. And they're wanting you to do I minus C inverse D. So what you got to do is you got to find I minus C. And that's the matrix I is, and this is a 2 by 2, so it's 1, 0, 0, 1, and then subtract that C matrix, and the C matrix is so then this is 4.9, and then subtract and minus 0.5, and then this is 0.8. Now, if you go back and rather than doing the inverse by converting the I, the matrix I, and then making it so that you have I matrix for a 2 by 2, you can go back on 105, page 105. This will only work for 2 by 2s, and you can use that theorem 4 on 105, and it says if you have that matrix, then the inverse of that matrix is I minus C inverse is going to be 1 over AD minus BC, the determinant, times D minus E. This is D, but I'm root A. D minus D minus C A. Where this one is A, B, C, and D. So it's 1 over A times D would be 0.9 times 0.8 minus B times C is negative 0.6 times negative 0.5. And then what you have to do is you have to do 0.8 and 0.9 and do a minus of this, so this is going to be 0.6 and 0.5. You just got to figure out this determinant. I think this is 0.72, isn't it? Minus. This is going to be plus. this wrong. 0.30, right? Isn't 0.6 times 0.5 0.3? It's half of 0.6. That has to be. It's 0.42. Now you just have to multiply it. I don't have my calculator, so when you have to do this. You have to do 1 over 0.42 times 0.8, 1 over 0.42 times 0.6. Yeah, what's it coming out? What's the upper left one? This one here is 1 point what? 9. Then what do you got across? What's the next to the right? Or tell me what you're calculating. Over to the right. Like that? So this is I minus C inverse. It's a little quicker than what we were trying to do last time. But you can only do it by 2 by 2 matrices. So if you get a 3 by 3, then you have to do it the other way. And now then we have to take that times D. So we're going to multiply 1.94 and 2.1. And the D matrix in our problem is 1811. So this is 2 by 1, a 1 by 1. So we're going to get a 2 by 1. So our first one is going to be the first row times the column. So it's 1.9 times 18 plus 1.4 times 11. And then it's 1.2 times 18 plus 2.1 times 11. Whatever that comes out to be.
49.6 and 4.7.
And 44 point what? And the answer is 50 and 45. So when you do it that way, you get an approximation of what the answer is. But if you do it the other way, you're supposed to get it exactly right. The way that we took a long time and didn't get it right. So, Okay, the problem 8 on 139, it says, let's see the n by n consumption matrix whose column sums are less than 1. Let X be the production vector that satisfies a final demand D, and the change of X for the production vector that satisfies the different final demand D. Change in D. And it shows that they wanted to show that if the final demand changes by D to D plus delta D, then the new production level must be X plus delta X. And delta X is the amount that the production must change in order to accommodate production. So, what we have, we're starting out once again with that the production equals the CX plus demand, and then we're finding this thing. So then we have X times 1 minus C. Or I guess I'll do it the other way. So if there's I minus C, X. These are square matrices, so they're invertibles. And then it's I minus C inverse X. Inverse times D. So that's what we have. And then they're saying, if this is the production, then if you have a change in demand, delta D, then you have to have an equivalent delta X to get that change in demand for D. So if you have your I minus C, and if you add to it delta X on this side, I'm taking this equation right here, then you have to have D plus I minus C. No, I don't want to do. Then you have to have 1 I minus C. And X plus delta X has to equal and you could distribute that across then. So that should show then that what you have to have is you have to have, when you're adding demand delta D, then you have to have a delta X added to the supply of goods. The B part says delta D, let delta D be the vector in Rn with 1 as the first entry of zeros, and then zeros elsewhere. I'm going to explain how the corresponding reduction delta D is the first column of I minus C inverse. And that shows that the first column gives the amounts of the various sectors must produce to satisfy the increase in 1 unit. Just by way of an example, what we have is that if we have if you have consumption units, and you ultimately get to the point where you have X equals I minus C inverse D. If you use just an example of a matrix A that is a 2 by 2, that's A inverse. And if it's a 2 by 2 where you go A, B, C, and D. And if you increase the demand here by 1 unit, that means that what you're doing is the demand for here is going 1 unit up, and all other demands are the same. So if this is your A inverse, and then you have it times a vector 1, 0, then essentially what you're doing is you're getting A plus 0B, and then C plus 0D, which is A, C, which is just this first vector right here. So if you increase any one of those, if you have an n by n matrix, and you increase any one of those by 1, so if you had 0 and then had a 1 here, and it went zeros on down, then whatever row this is in, it would pick the column out of the IC inverse. It would pick that column. So if this was the ith row, it would pick the ith column out of here, whatever that was. AI, BI, CI, whatever it is. And then these would not be in it, so it only pick this column. So what this is doing is this column becomes the amount that has to be produced by any sector when the demand for that sector is increased by 1. So if you take, I guess in this previous one, back here, this, in this particular one right here, where we're going, this is telling you right here how much must be produced for 1 unit increase in the sector, the first sector in the economy. So if you had, for example, ag and the producing parts of your economy were agriculture, the production, what was it? Manufacturing and services. So if you increased manufacturing, if manufacturing was the first item in the demand, then the column that represent manufacturing would tell you how much each one of the manufacturing, agriculture, and services would have to increase to produce 1 extra unit of that particular product. And that would be of this IC inverse. And that's what they're trying to get to, is so that you understand that IC inverse is actually the production to produce 1 more unit of output in that particular sector. Okay. Number 10 says the consumption matrix C for the U.S. economy in 1972 has the property that every entry in the matrix I minus C inverse is non-zero and positive. What does that say about the effect of raising the demand for output of just one sector of the economy? Well, if I see, if this I minus C inverse, and if every entry in this thing is positive non-zero, it says that if you increase the output of any sector by 1 unit, every sector is affected. Every sector must increase its output. If any of these were 0, then it would say that you would not, that sector would not be affected if it was related to say that this was a 0, then if you produced an increase in the second unit by 1, that this sector would not have to produce anything extra. But if they're all positive and non-negative or non-zero, then every sector must produce more when demand increases for any one of the products. Okay. I'm going to skip to 7 and look at 2.8. And this is subspaces. So it says a subspace is any H that has the properties, the 0 vector has to be an H, and that U plus V has to be an H, and that the scalar multiply times the u has to be an h. And they say that the best way to visualize that is a plane through the origin. And that's because the zero vector has to be in there. In the example on page 149, notice that that line can't represent a subspace because it does not go through zero. So the zero vector isn't in that line. Then a column space, the definition on page 149, matrix A is in the set column A of all lines, combinations of the column of A. So that's just the definition of the column space. And then we're going to talk about a basis. It's a linear independent set of H that spans H. What we'll do is we'll do some problems. That theorem 13 is important because it's talking about the pivot column of A form the basis of the column space of A. So if you have pivot columns and it's linearly independent, then you will have column space. If you look on page 153, and it says that the display is an R2, two-dimension. Assume that the sets include bounding lines of the space. In each case, give us specific reason why the set H is not a subspace of R. Okay. Now, number 2. It's saying that you get all the values here and here. And what you can do to show that it's not in the subspace, you could take the vector this u and the vector here, which is v, then u plus v should be in the space. U plus v would be right there. This would be U plus v. And notice it does not fall in that space, so that cannot be definition of a subspace in 148 is not met. B is not met. All scalar multiplications of these vectors u and v fall in that space, but there is an example of a scalar addition that wouldn't fall in there. And not all scalar additions don't fall in there, because if you had something like this, so that your u is here, then your u plus v would be there, and that would be in the space. But not all u plus v's are in the space, so it can't be a subspace. And 4, it's actually a solid line. It goes through 0, so it meets the null, the 0 vectors in there. But um, um, what the problem is if you did a scalar multiplication, if you put a vector out this way, call that u, and then if this was u, then if you did a minus u, minus 1 times u, then you would get that, and that doesn't, in the part that they're talking about that is in the space is all of this stuff. So the scalar multiplications don't all fall within the space. All the additions fall within the space. If you have two vectors in the space, their addition falls in the space, but the multiplications don't all fall in the space. So that's what you would look for is that definition on subspace. See, the zero vector is in there. It's in there. Likewise, the 0 vector is in here. But the rest of this one, addition is not all addition is in there, and this one, not all scalar multiplication is in it. So the definition of subspace isn't met. Okay. That's 6. Six says V1, V2, and V3. U is equal to that. Determine that U is in the subspace generated by V1, V2, and V3. Okay. Now on page 149, example 4. And right above there it says, that statement says, if A1 through AN is a vector with columns Rn, then the column A is the same as the span of A. And example 4 shows that the column space of a n by n matrix is the subspace of Rm. So what we have to do is do it like example 4. And you notice that what they do is they get it in echelon, and then they find out that you have I don't know why I cannot get it out of my head. Turning points. You have pivot points. And you have either pivot points along the diagonal or you have free values. So that's what you're going to have to do with this, is write it in vector form. And then you have to have a diagonal of pivots, or else you have to have zeros. So what we'll do is we'll take this thing. 1, 4. So this is going to be B1, B2, B3, and U. So we're multiplying 2 times that, right? So this is going to be 1. It's going to be a 2. That's going to be a 2. Did I do it right? And I'm multiplying minus 4, so this is 0. 16 minus 7. 20. Multiply minus 3, minus 12, 15, did I do that right? Okay. Now what I want to do, so now I'm multiplying by 7, 0, 14 is 0, 2 7s, 14, 23, and I'm multiplying by 5. Now, these are not linear independent, right? So they're an inconsistent set of equations. Inconsistent. I don't have to accept twice. And say that U is not a subspace of V. They would have to be free. If they were free variables, then we have the 2 turning points. If we had free variables, then it would be. We don't have the free variables. So 8 this is the V1 through 3, and P equals that, and they want to determine if P is in column A, where A is V1, V2, V3. So what we do an A, P, and we're going to have our vectors V1, V2, V3, and then P. And then the P is 1, 2. And then we want to show that we have pivot points for free variables. So I'll multiply that by 2. And then I'm going to multiply by half. So 1/2 of that is minus 0, 0. So what I have is it is a consistent set of equations. So P is in column A. Okay. I'm gonna quit there. I'm gonna give you a quiz.